let's start to the next talk. Cloudlessly secure does this really necessarily have to be put into the internet? Well, Christian Amsus has been active in the free software movement for 15 or 16 years, so pretty long. As he's also working with sensor networks and stuff like that, which is all very interesting and useful, but in many cases it's a question, does it actually, all of this have to be routed to some provider on the internet, where in worst case just everyone can, or anyone can actually get those data? So Christian, please. Hi, thanks that I can be here. Well, yeah, Albert already mentioned the introductory words, so I'll start directly with what I want to talk in, in content-wise. So, what around us, which things around us actually connect to the internet regularly, especially in the IoT, right? Why do they do this? And is this actually necessary that those devices do this? Especially I want to talk about technologies which help those devices to make to do what they are produced to do. So, and why these things could be done locally as well. Actually, could be. So I'll talk about some basis technologies stuff of IoT, so Internet of Things stuff. So, and then work up from there to have a look and to show what is possible with these IoT devices. So let's start with a concrete example, just like a vacuum cleaner, where you think, well, you see, in general, they do what they can, but sometimes they get apps which have like additional services, which offer additional services. Like I can see on my smartphone, like the layout of my flat, where the robot is going, so the vacuum cleaner. Experience shows that most of these apps only work when I have internet connection, which is advertised as, yeah, Wi-Fi access, etc. And usually you usually don't have a differentiation of what is Wi-Fi and internet. So in the graphics, you see the Wi-Fi is just the lower part. So you have the rover, the robot, the network, and the router, and the smartphone, and actually all of them are in the same network. So actually, you don't have any necessity to go into the internet with that. So of course, there are other devices like your AC, lightning bulbs. So they usually talk with each other locally, but still, then maybe sometimes don't start if they can't have an internet connection, despite usually usually talking to each other locally. So another example is AC or just anything, heaters and coolers, which also like to work over the internet, and a lot of other stuff in your kitchen, for example. So usually they can talk locally, but they need for some reason internet. So the question is, do you really need them? So when we're talking about the cloud, so those things connect to the cloud. So but what is this? So actually there's more than the cloud. Maybe you see this t-shirt, you know this t-shirt from the Free Software Foundation, which says, so there is no cloud, just other people's computers. So actually, that's the point. So you just have servers. So it's not just this nice little fluffy cloud, but actually you have servers. So the cloud has long been used to depict networks which you just go through, and you want to arrive somewhere else. And we will talk. Still, I will talk about building up communication with the cloud, despite actually there is no cloud. So I'll just use it still as a word. So you can see even those single servers are actually usually just like a group of servers. So, but still, it's not our servers. It's still other people's servers. So, like usually from the manufacturer. Okay. Well, I have two more things I want to mention here before I really start with the technology stuff. So first one is, where do we focus here? There are a lot of devices. When I talk about embedded systems and IoT here, I usually mean small devices, like small factor, not just physically small, but also like light bulbs, light switches, um, of course, ACs and heaters also they have things like Raspberry Pis built in there, but usually um, usually we also want to include devices which cost only cents when they're manufactured, like it's really small devices. Yeah. So yeah, now he's talking about production and whatever, so it's not so. But we focus on small devices, so that's the point. So this doesn't exclude systems where real Linux is running, but usually I just want really embedded systems. And the other thing is, what I don't want to talk about is networks which are not connected directly to the internet, but use a application-specific gateway. Especially in the last years, this is rather common in the IoT devices, so that you have like one device which connects to the rest of the device, which connects to the internet, and all the other small devices actually connect to this device and not directly to the internet. For all of the things, usually you have like the same things apply, but I just don't talk about them because now the communication between those devices and the gateway device, so usually the communication is between the devices and the gateway, and then the gateway and the router, and then the router and the internet. So whatever you can say about the small devices, you actually have to talk about the gateway itself and not the devices, because only through the gateway they can talk to the internet. So why is this happening? So talking about to a manufacturer, you usually say you don't get any information because they say for security reasons. When I talk about the protocols, this is actually not really necessary that they talk that it's a security risk. And I also looked at like more open cloud protocols and checked what they can actually do. And the one what I went concern about most is Lightway M2M, which is a protocol, a communication protocol, which is used for like remote maintenance of devices. So all those devices are there put more transparently, so users can actually see into what happens, and you don't have to talk to the manufacturer, and it's not like as much vendor lock-in with this. So first thing I want to talk about is firmware updates. So devices will have vulnerabilities from the start, and people will find vulnerabilities later, so you need firmware updates. Without firmware updates, security is impossible, and no one can guarantee that there won't be any mistakes, found. So firmware updates are really important. Why something wants to talk to the cloud, because it needs firmware updates. So this is something. Next one, a rendezvous point. So this is addresses where two devices which want to connect, especially about IPv4, and where they want to meet, because they can't directly connect to each other because they don't know where they are. So they have one point at the internet where they can meet, and this is like the rendezvous point. So this also may be a point why they need to connect to the internet. And if then still a direct communication is not possible, you always have like a circumvention communication. So two devices, they may be in the same network, but still they don't talk directly to each other, but they load their commands and data. First they load them to another server, load them up, and then the other one download it from there. So I'll talk about this specifically because usually that is for security aspects very relevant. Because if I trust the other device is a very different question whether if I also trust the server in between of those two. So you just have a third party in that setting. Let's talk about trust. So when two devices talk to each other, usually they have to have the rights to push their data, pull their data, whatever. So they have some kind of authentication or authorization, which I just summoned up as user or account management. So in that case we just talked about, this might mean that like you can have like a guest user for your vacuum cleaner, or a user which may like be able to start the vacuum cleaner but not read out the data and stuff like that. So account management and can be also like time constrained. So it's also important that the system knows the current time, because otherwise you can't make time restrictions. Something else is like the collection of data, aggregation, and like so to react to things that happen on the internet, like stuff that comes from the internet. So like crowdsourced radio measurements, or if a server process is failing, the IoT device wants to connect it, but those things I actually don't want to talk about in this. So like no analysis of aggregated data, reactions to data from the internet, and EULAs is stuff I don't want to talk here, because this is necessary if you're doing cloud. But the question here is, do you actually need to do cloud? So why do we actually talk about this? This cloudlessly secure. One thing is like just redundancy and availability. So usually it can be just internet fails, or like, but it also can be like internet censorship. It can be internet cuts, which is also into autonomy. So can I do something with my system which I actually should be able to do without having to rely on third parties? So here in Australia we don't have these problems with censorship and internet cuts, but in other countries, looking at like American trade sanctions against Iran, or so people in Iran suddenly can't use US cloud service providers, and so this is where we are here. So, and that's again, of course, don't getting too much data, and don't collect, no over collection of data. So, system which doesn't collect, which doesn't talk to many other systems, maybe in some cases less usable, but it also loses less data if it doesn't collect so many. Before I start the concrete points here to talk about the single problems, I would lay some basic technologies which have been like established in the last 10 years, and which have been
So I put this into this kind of stack diagram. This is not everything I'm going to mention will be building upon each other. For example, the constraint application protocol can just as well be used via TCP, not UDP, and the concise binary object representation could just easily be used as a file format and a data representation format. But it's a good point to start with these building blocks, not least because the analogy to what you know as the model for the large web with the web browser and that kind of thing. So we have quite a good analogy here. And semantically, this is quite similar. And it covers Internet of Things devices just as well as HTTP covers browsers. And CBOR is more like a translation of JSON, simply adapted to this particular purpose. It has many applications. We'll look at this a bit more in detail. I'm not going to talk much about the underlying protocols maybe in only for some details, but generally I will believe that everyone watching the stream has at least used these protocols, even if they don't know them in detail, because IP, of course, is the protocol that that is used for live data. I don't know which protocol is used for that a lot. HTTP surely as well. Back to the constrained application protocol. Excuse me, there was some disturbance, some problem with this original sound there. So we may be talking about details, graphical elements, but largely it's a very clear equivalence up to the point where they may actually be converted into each other. Now, in the next slides, I'm always going to have this line at the bottom, and that line tells us how widespread these protocols are and what the references are. And everything I'm going to talk about is developed by in the framework of the Internet Engineering Task Force. This is a loose association of people that design protocols on the internet. So compared to other standardization organizations, this is a fairly open group of people, and they can be accessed through things like mailing lists. Many of the standards are simply there on GitHub, and you can actually suggest changes. The individuals that write these often are employees of large companies, but they are individuals still, and the working group then eventually, there's a good process going through the group leaders and experienced protocol developers, which then check these standards before they then end up in one of these famous RFCs, which are numbered. So everything from the internet protocol via HTTP, what we use these days on the web, is specified there. So just that much about that bottom line in my slides. And and this co-op standard is described in RFC 7252. And the naming is fairly modest. Just because something is an RFC, it's not necessarily an internet standard. It can go up a certain ladder. It can progress from something with experimental note, something like an experimental note, to something like a standard, what you would assume to regard as a standard. A proposed standard, and then it can become an established standard later on. One detail perhaps about co-op compared to HTTP, which I used in my equivalence, this can very much adapt itself to the network in use. So if we go back to the network diagram, it could be Wi-Fi, there could be other networks, mesh networks. Co-op can use all these things, can be used on all these things, and it has adaptations. And much more than HTTP, it can use proxies and can be implemented in various forms. Multicast, for example, for discovery is one of the features that comes from the requirements of the Internet of Things and is supported. So multicasting means that if I have a control, I can For a light, then I can switch a number of bulbs with a single switch action, rather than addressing each slide in each switch individually. There are one or two building blocks that I won't go into much detail about. CBOR is the equivalent of JSON, semantically just like CoAP, and every JSON document can be trivially translated into CBOR. It becomes smaller. It can deal with binary data, and not least, it's simpler to transmit to devices with small storage, such as 100 kilobytes or less. And COS adds something to it, such as encryption and signatures and checksums that can all be processed through COSI. That isn't as widespread if you look at the number of implementations in the bottom of the slide, but if you look at the number of devices, then you will see that practically every modern computer uses it, because web authentication is one of the applications. So all those small USB sticks with which you log into a website with two-factor authentication and not with a password, they use this, and that is based on CBOR as well. Now, on that basis, we can see how the requirements for devices that want to talk can be deduced from that. I'll start with suit. That is a draft still. So we're leaving the area of what is a definitely at least proposed standard. Suit hasn't gone through the whole process yet. Suit is an architecture for software updates that doesn't just describe what the firmware is supposed to look like, but also the processes that are supposed to run. And that distinguishes it from what normally happens in firmware updates. The various participants in the network are explicitly taken into account. If we have a network like the one I've described for my example with a robot vacuum cleaner, you don't just have one device in the cloud, but that device has an owner and an operator. And the decision whether a device is supposed to receive the latest firmware or whether it's not so urgent at the moment, and it might be doing an important job at the time and shouldn't be updated right now, that decision, of course, should be left to the owner. And Suit supports this explicitly. Suit has another important aspect. It's independent of the way the firmware is transported. It doesn't necessarily have to be the case that this robot vacuum cleaner connects to the cloud server. It could also get the firmware update from the mobile phone that controls it, which could run the app for the vacuum cleaner in a more modern version. It might use some features and want that require the firmware update in the robot vacuum cleaner, and there doesn't need to be an internet connection for that to happen. And the authentication that the firmware is the right thing for the device, that it really comes from the designer or from whoever has the role of issuing new firmwares, which might be the user perhaps, but in practice we're a long way away from that. That can all be modeled in this format, and these rights can be communicated as well. Another component that is important when we talk about devices communicating with each other, these are fairly boring examples, two overused examples, the light switch and all that that is the prime example for IoT applications, although in practice you may find very different devices, but let's stick to those examples. Now, for these devices to communicate with each other, it needs a certain security layer. We had the option of encrypting data, but in most cases we want more than just securing the content. The whole communication up to the point of who communicates with whom should not be seen by outsiders as well. And if you want to protect more the who with whom aspect, then we are back to the talk 2 ones before this one about the one about Tor. This is not delivered by these protocols. But back to the question how we can secure this. There is a security layer that has also been published as a layer, and it's called OSCORE, Object Security for Constrained RESTful Environments. This is again based on CoAP, but it gives the application that uses it the same semantics. So if an application is used to asking a light switch to change and getting a response, then OSCORE can be put underneath that as a layer and secure this. And this is generally also possible, and generally just as well possible, one layer further below, which is what we know from the large web, where HTTP is normally secured via TLS layer, which is below the application protocol and the transport protocol. That is possible in principle too, but I'm now focusing on OSCORE for 2 reasons. It's easier to explain where do the entities come from that are used, and also there are many applications that, because the things that OSCORE can do can be also forwarded to the applications easily, such as multicast. And I'm going to jump back a few slides because I think it makes sense here. We had the issue, the topic of proxies earlier. A TLS connection normally goes straight to the next proxy, unless, well, if it's not a SOX proxy, that is not a proxy in the actual sense. But we've seen that proxies are important in CoAP to adapt to network characteristics. If messages are communicated through a mesh network, then they have to be much smaller than the kinds of messages that I would exchange with a smartphone. They might use very different transport media. And the nice thing about OSCORE is, because it is built on top of CoAP, I can still use these mechanisms. So even if the communication uses a proxy like that, I can still, from my smartphone to the individual bulb, I can still build a secure connection. I don't have to rely on an intermediate device to tell me that the connection is secure and trustworthy, and then I have to believe that device. I don't have to do that. We were talking about communication detours as well. Even if we have a scenario in which communication has to happen through the cloud, because perhaps my mobile phone, a bad standard example, but I may be on the road with my smartphone, and I might be wondering, is my stove still on? So I have a connection to the internet, but not in the local network. And OSCORE delivers or enables me to still use proxies via 3 hops, but still get a secure device up to all the way to my stove, and then to issue that question without compromising security. What OSCORE, in contrast to the transport secure layers, what OSCORE does not have is key negotiation and the option of using asymmetric cryptography. So if two devices have agreed to use a certain key for communicating, then they will use that key, and they cannot generate a new key or agree a new key, and they cannot attach different rights to that key. The key is there for this connection from device A to device B and nothing else. But that, again, is an advantage. We were talking about small devices, less than 100 kilobytes of RAM or flash storage. All those processes may not be practical there. So if there are other protocols that enable that key exchange, that might not be an option. And another thing that's fairly early in the standardization process, which is called LATE, that deals with the whole asymmetric cryptography issue, to ensure that even if the old keys are compromised, then the communication can remain secure. And about the topic of user control and various access rights, that is much more relevant to have a framework there. It's called authentication and authorization in constrained environments. And that can take over many of the tasks that I've described as user administration earlier. ACE, compared to the protocols in the large World Wide Web, is perhaps best matched to, I didn't get what it is closest to. That is for building a secure connection by having a common contact point. In the ACE terminology, OAuth is so this equivalent of OAuth. There's a resource server, and that is connected to, and ultimately a token is retrieved somewhat related to a username and a password from an authorization server. The resource server, the device that is actually being controlled, also has to have a connection to that authorization server, but it doesn't necessarily have to be an active connection. It might just as well be a connection that happens in the factory, or at least at a much earlier time. It may not be necessary right now to be able to have the client find the resource server. To use another example from cloud communication, if I have my device that from the factory is only going to listen to the access rights given by the manufacturer, then via ACE, I can use my smartphone in the local network and authenticate to that device and hand over a token to initiate a secure connection without having to reconnect to the server, simply because my device did once get that authorization from the authorization server, and using that token, it can tell the control device that it belongs, that it has the right to do certain things. But the device no longer belongs to the manufacturer, it belongs to me now. And the nice thing about the ACE architecture is even the authorization server is a role. It's called a server. And we're talking about servers when we mean devices, but that authorization server is nothing that requires a server in a data center or a database. It can be just as well be embedded into the device, into some device. So it is possible there to have in the local network as the device is put into use, to take control of the device, and then when a heater is used and then later a thermostat is used, I can tell the thermostat that it has the right to connect to the heater, to the climate device, and that it can deliver a current temperature measurement to the climate device without a single connection, further connection from the smartphone. And what's important with these tokens also is that they often disappear in the clouds, and they only need very lean authorizations. If a token is issued, then this token will contain the information that it is authorized to set the current temperature at a certain climate device, but it does not have the right to install software in or to switch it off and so on. So the options are there to negotiate these rights between the various devices without having to have a large authentication system in the background. And now that I've heard that I'm nearing the end of my time, this is a good time to summarize with regard to the requirements that we had. So firmware updates, they can easily be done in a local network. They do not require that the device communicate with a manufacturer, and still requirements that a manufacturer may have. For example, only authorized firmware is allowed. That can be implemented. If you want these kinds of requirements is another question, but it's possible. No one has the excuse that that kind of control would be lost if you could take the cloud away. Regarding rendezvous points, I didn't talk much about those, but because CoAP has this multicast option, devices can find each other. And for real-life applications of internet communication that has to use the outside internet, the intermediate devices that once have got to know each other can be set up in a way that no trusted server, not a server from the manufacturer, but some device that maybe the user has configured, and that a third-party suppliers can allow this communication, and you can still not look into the communication. User administration, well, ACE is not a user administration. Access rights that require various identities or personas or whatever. I'm not aware of any implementation for IoT devices there. Although there are components, but it's not necessary anyway, because the underlying mechanisms can be built in such a way that any kind of user administrative task and the rights that come from that, the rights can be communicated anyway without all the devices where these rights are exercised having to communicate with a third server. So I would like to summarize by saying that IoT devices can be built without the obligation for them to go online. So demand such architectures. If the makers claim that this is not possible for security reasons, then maybe it is the case because they don't know these components, they don't want to use them perhaps, or the development time that they've invested demands them to take a different course, but it's not a technical necessity. Right. That's it from me. And I'd be happy for any questions. How about the break room? Mute is a dog.
Okay, so there's one question I have already, and I want to ask you here. So I suppose it's very basic to what you just talked about, but it's a very basic problem, which is, the question was, what can we do if the manufacturers don't have any offer any firmware upgrade, but there's no budget to upgrade your devices or buy new devices? Good question. Well, my personal opinion is that this is something which you can have, like, you have two approaches which are possible. The one is the power of consumers, so only buy devices from manufacturers where we can trust that they regularly provide firmware updates. I don't know how well this will work, but the other approach is which I would prefer is political, so to go via politics. So manufacturers just make manufacturers liable for creating firmware updates, and if they don't provide firmware updates for the time they actually have to do by law. So like if you have just a warranty, basically, and then you can and so then they have to, so if they can't provide any more updates, they could